Welcome. This is the first computational lab for this course, and the objective is to give you a basic feeling for the R programming language and to do some basic functioning like reading data in, exporting data, exporting graphics, and doing some plotting and so forth. So to get started, you'll need to install R, and the best thing I think is that if you work along right with me. So when you open the R console, you're going to see something like this. And what you're going to want to do first is you can type things directly into this command line, but you want to have a record. So you want to open a new document. So File, New Document will bring you up a new blank document. I've created some text here. I usually do this at the beginning of all of my codes to say what the code is, who created it, myself, when I created it, and when I edited it. If you do a lot of programming, this is critical from the point of view of staying organized. What I also do, and I encourage you to do, is I put comments throughout the code to tell me what's going on, and that's useful also when you go back. And it's useful in this course because I am going to have to read it, so I just would like to know where you're coming from. And so this pound sign means that if I copy and paste this into the console, nothing happens. It doesn't execute it. It's for text. If you want to clear the console, you can go to Edit, Clear Console. Now, you can clear the console, but everything is held into memory. And so right now there's nothing in our memory because we haven't done anything yet. But often the first thing you want to do is you want to clear out the workspace. And to do that, you're going to use list, this command here. I put this at the beginning of all of my codes. Now the workspace is empty. And sometimes if I'm running R for a long time, I'm doing different things, I just want a clean slate, this will do it. Okay? Now, I may have some data that I need to read in, I may have some things I want to read out. I want to save this file into a directory, in which I've done that already. It's called pre-mining examples.r, and I've made a folder here on my desktop called codes, and it's in here. And I'd like that directory to be where I go to between R. So everything that's coming out is going to go in there. Everything that's coming in should be read in from that location. So to set the current working directory, we can just use set word, and you write the extension. It will be different. Now I use Mac, so my extensions always look a little bit different than Windows. And my folder is called codes. Okay, so let's change the directory. Okay, so now we're in good shape. And the thing about R is it doesn't come preloaded with the libraries that you need. It does have a core set of functions and features. You do have to do some installation along the way. So install some packages, and the way you can do this is just by using this command. This command is good if the package is on CRAN. Okay. The packages we're going to need today are DAG, Lattice, and Mass. Okay, so let's see what happens. Okay. It's installing, it's downloading. Okay, they're downloaded. Now, I'm just going to take these right out because I'll comment them so that you have them. But once you install a package, you don't have to install it again unless there's a version update. Instead, you can just load them. Okay. Okay. Lattice and mass. Okay, so let's load these in. Okay, so now I've called the libraries that I need. Now there's one other library that we might use. So let me just open up Firefox. This is typically how I find libraries because sometimes I don't know if something's in CRAN or if it's in Bioconductor or where the function is. That's kind of the trouble. It's called GenePlotter. Okay, it's in Bioconductor. When you install from Bioconductor, it's a little bit different. You can use these two commands. Source will bring you to the website itself. Bioconductor it's this biolite.r. And we want to install GenePlotter. So let's just copy and paste that right into the command line. Now, if GenePlotter or whatever package you are, I'm just going to update everything. Whatever package you're installing, it will always look to see what the dependencies are and install those packages as well. And any updates, that's what it just asked me. So now GenePlotter is installed. And we can call it. Okay? So let's get started now with some basic plotting. I'm going to just block things off into sections. That's typically how I do things. So this is going to be histograms and density plots. Okay, so these packages that I asked you to install, they have a lot of functions in them, but they also have some data. One of the data sets is called Possum. So let's take a look at that data set. This is how you do a help. Question mark and the function or the data, whatever, and it will bring it up in this pop-up window. And so this means that this data set is part of the DAG package. Here's a description of it. You have 104 different possums, and you have different measurements on each of these possums. These are the measurements and so forth. So, okay, let's try to get a feel for the data. I think about things in terms of matrices. This is 104 rows and 14 columns. 14 being the measurements, 104 being the different possums. Now suppose we want to just take the female possums. Let's grab the females. Well, I'm going to call that object Fossum, and it's a subset. And let's see what let's do names possum. Names is going to tell me each of the different measurements that was taken. And so, sex is one of the names. So let's subset by sex. Sex is female. And we're going to be subsetting the possum data. You have to tell it what the data is. You could do a question mark subset to figure out exactly how to do this, the different fields. Okay, let's grab the females. And now, say we want to export that as a text file. Okay, we want to write a table, Fossum, and let's write it as a tab delimited, or let's do file is equal to female possum data, and sep It's going to be a tab delimited file. And let me just do a question mark right table to see what the other fields are. Row names and column names we should specify. Okay. Let's say the row names are false. I don't want row names. But let's say the column names are going to be the names of the columns in the possum data. Actually, we could just write fossum because they carried over. Okay, so let's execute this. Okay. Now if I look in the codes folder, which might be small for you to see, I can see that the female possum data is in fact here, and it's just as we wanted it. Okay, it's a tab delimited file. Now that's for exporting data or exporting a table. Now suppose we want to read the data back in. I'm going to make an object called temp, and I'm going to read delim. The file name is fem possum data.txt. And it's a tab delimited file. And header, it does have a header. Okay, so once you use these a couple times, it's pretty easy. I'm going to rewrite this because I forgot the text extension, so let's see. Okay, so now we're all set. So if I look at temp, it should be an exact image of the fossum data set. Okay, so I'm just going to comment these out because it's kind of an aside, an important aside. But now I'm going to work with this fossum data set and plot some histograms. So I have in mind here to do 4 different histograms. I'm going to do the first 2 histograms, just doing regular histograms with frequency, and doing different bins, different types of binning. And for the last 2, I'm going to plot the density over those. So I'm imagining here, again, I always think in matrices. Kind of 1 row and 4 columns for the plotting, okay, for the 4 different plots. And the trait that I'm going to focus on is the total possum length. Okay, so you can do a question mark hist to see what that involves. But I'm going to set the breakpoints myself, although you don't have to. They will do it for you. But I'm going to start at 72.5 and I'm going to increment and I cheated so I know how to set the y-axis, but again you don't have to set that. It can do it for you. And for my x label we're looking at total length in centimeters, and the main is just the title. This is plot A, and it breaks at 72.5, 77.5, and so forth. Okay. Now I'm going to do the same thing almost. In fact, I'm just going to copy and paste. Okay. I'm going to change the breaks. We're going to start at 75. And I'm going to call this B. Okay. And let's just take a look so far. Okay, so I have 2 different histograms here. and I have set the breakpoints. You can see that they look a little bit different. This one kind of looks asymmetric. This one looks a little bit more symmetric. Whatever, it's for a reason. So, and there's 2 open spots here for 2 more graphs. Okay. And so let's look at density functions. Well, first we have to do a density approximation. You can do that with the function density. Total length. Okay. And I want to set the limits in the histograms. So I'm just going to set those limits according to the range of the density in X. And the Y limit can be the range and the density for Y. Okay, and so now my feeling is that I'd like to look at the density functions plotted right over the histograms. So I can do that. I'm going to copy and paste this one. Okay, the breaks are going to stay the same. I'm going to put in a statement here called probability is equal to true, because I don't want to see the frequency count anymore, because I want to deal with this density. The X limit and Y limit are going to be defined according to the density. So let's change that. And let's see, is there anything else? That's all fine. Let's do the same thing with the second one. Okay. So the breaks now are at 75. La la la. The probability, X limits, Y limits. Okay. Now we've got to change this to B. And these breaks are at 75 and 80 and so forth. Okay. Okay, now I said I wanted to plot the density right over there, right over the histogram. So the way you can do that is just by doing lines, and we've called it dense. So we're going to do that for each one of these. Okay. And let's take a look. Okay. This is what it looks like. All right. So we have the 4 different panels, and we're kind of getting a feel for this is giving a little bit better of an indication of what the distribution is looking like, these density curves. Now, say that I want to export this into, you need to put this in your homework, for example. You can take advantage of this package called GenePlotter. So let's do save EPS. Okay. And let's call it something like density plots. Okay. Okay. Okay, it did. And where did it put it? It put it in the directory. You can also, the nice thing is these functions will link to other things that you might be interested in, or it tells you things like save PDF, you can do that, EPS, PNG, and TIFF. Sometimes they can link to different functions that may be of interest as well. So it's useful to look at the help. So that's all you need to do. You can just throw that into a Word or a LaTeX document and you're done. Let's see here. Okay, so that's kind of it for the density plots. And the other thing we talked about were stem and leaf plots. I'll show you how to do those. Stem and leaf plot. Okay, so there's another data set called AIS. So let's do a question mark AIS. Okay, again, it's in the DAG package, and this is blood by sport, body size, sex of athlete. Okay, so let's see here. Let's do names AIS. Okay. All right. So sport. Let's look at AIS sport. Okay, so these are all the different sports. What I'm going to do is I'm going to create a subset that grabs all the rowing data. So let's grab the rowers. So I'm going to do it in the same way. Rowers is going to be subset AIS sport is equal to row. Okay. Let's take a look. Okay, let's just look at the data itself. You know, sometimes if I want to get a look for the data and it's too long, it's hard to see, I'll just look at the first 5 rows or so, and you do that in matrix notation in this way. Okay, so this is just a little clip of the top of the data. So it's all the rowers, dim rowers, 37 of them for 13 different measurements. And let's make a stem and leaf plot. Okay. Stem, rowers, and let's make a plot of the height. Okay. Aha. And this is what we saw in the presentation. So another way of looking at the distribution, we can kind of see there's an outlier here and so forth. So that's pretty straightforward. Let's do box plots. Oops. Okay. Another thing that might be useful, another command is graphics off, which closes all the graphics windows that are open. If I want to open a new window to do a graphic, I can use Quartz or I can use X11, something like that. Macs have trouble with the X11, at least in Lion, so I'm just going to stick with Quartz. This opens a graphics window. So now this window is open and waiting for my graphic commands. So let's do a box plot. Let's go back to the FOSSUM data. Let's look at total length. And I want horizontal orientation. So horizontal is equal to true. Whoops. Okay. You may have heard that little beep. It will tell you if you're having a syntax that doesn't make sense sometimes. Okay. Here is the box plot for FOSSUM, the female possum data, and we can put in something like this. box plot female possum total length. Okay. Oops. Let's see. Oops, I forgot my equal sign. Okay. So that's it. And you want to save that, you can just use the save EPS or save PNG and so forth. Okay, let's take a look at when we have more than one trait. We want to look at things together. So let's just look at patterns and bivariate data. Okay. So there was, let's look at another data set called milk. Okay, and this is also in the DAG package. The milk data has 17 rows and 2 columns. Each of the 17 panelists compared 2 milk samples for sweetness. And let's just do a really simple plot. I'm going to say the XY range. I'm going to do a square plot, so it's going to be the range in the milk data. Okay. Now, let's just plot. Let's look at names, milk. Okay, 4 and 1. So these must be the names of the measurements, which is a little bit confusing. But let's go ahead and plot 4. This is another way of writing things. 4 would be like the explanatory variable. And we have 1. The data is milk. The X limit is the XY range. And the Y limit is the XY ranges as well. So we're just going to get this square plot for symmetry. And for the main title, we'll put milk sweetness. Now, PCH is equal to 16. This is what type of marker you want to use. So if you as I mentioned, R isn't great for graphics, but if you do help par, if you forget par, do help plot, and it will link you to par. There are about 1,000 different parameters here that you can set, and PCH is one of them. So let's go down and find PCH. Yeah, an integer specifying a symbol or a single character to be used in the plotting of points. Okay, you don't have to set that. I'm not sure what the default will look like, but 16 is a good marker. And then I also want to set the rug for each one of these. And I'll show you what that will do in a minute. And let's plot a line with intercept 0 and slope 1, AB line. Okay, let's see what happens here. Okay, here's milk sweetness. Okay, so we see there's a linear trend. And this rug command that I did puts these ticks underneath. And I can see I did this wrong. I should say we want them under both. Let's close this and redo it. Okay, yeah. So for each value it puts a tick and so forth. It puts it all on the floor, but that's useful as well. And we'll put the line in too. Okay, so that's just one basic plot. Now let's look at something else. Let's look at another data set and fit a smooth curve. Okay, so we will do fitting a smooth trend curve. Okay, so for this data set, we'll look at fruit ohms, fruit ohms. Okay, so we're looking at electrical resistance of fruit, which is kind of different. And let's look at a plot of ohms versus juice. Okay, so we're going to do it essentially the same way. Plot ohms as a function of juice. And for the x label, I'll let them decide what the range should be. Apparent juice content in terms of percentage. And the y label is going to be resistance in terms of ohms. Okay, and the data is going to be fruit ohms data. And we want to add a smooth curve. So let's just do with fruit ohms. We're going to add a line. And we're going to use the lowest function to approximate the smooth curve. Okay, comma. And I think I need one more. No, that's good. Lines is equal to 2, so this is like the width. And let's see what this looks like. Let's open up our new window. Okay. Okay, there it is. So here we have the line. And if you look here, you can assess some features of the line and so forth. You have to do a help for Lois. And let's see what else we can do. How about looking at the appropriate scale? Okay, so let me copy and paste this. Whoops, edit, undo, copy, paste. Let's look at scales. Okay, so let's look at brain weight versus body weight. So we'll look at this in two ways. So let's pull up I'm going to have two plots side by side. MF rho is equal to C12. And I'm going to set PTY to a square. So again, if you do the help par, PTY is the plotting region. I want it to be a square region. So I'm going to plot now the brain data against the body data for the data set animals, which is also in the DAG package. Then I want to plot the same thing, but let's just do the log. 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 Okay. So let's take a look. Very simple. All right. And so here we can see, this is what we showed in the presentation, that the logarithm, you can reveal this trend in the data that you wouldn't see otherwise. So, okay. And let's look at patterns in group data. So we're looking at that cuckoo bird data, and the length of the cuckoo eggs. So let's do the same thing we did before. Let's keep it, we want two plots, square plotting regions, and let's do a strip plot. I'm just going to give you a series of box plots. We have species and we have length, and the X label is going to be the length of the egg in millimeters, and the data is going to come from the cuckoos, which I believe is also in the DAG package. Okay, and let's do BW plot and see what that gives too. Okay, copy and paste. All right. Let me change this. Let's not do this. This might be throwing things off. Let's just do quartz and quartz. So two separate windows. Let's see what happens. Okay. All right, so here I have just the dots themselves, and here I have the strip plot. Okay. And we can add titles, whatever we want to do. Okay, I have two more things that I want to show you. Let's take a look at comparing density plots. So we already did the density plot in the most basic form, but now let's say we have some covariate we want to take into consideration. Density plots. Okay, so these are from the Lattice package. We can do density plot, and we have ear conch, and we want to, that's going to give a measurement, and we have, this is for the possum data, so it's a measure of the ear, and we want to divide it by sex. Okay, so break it down by sex, condition on sex, and the groups, population, the data is going to be possum, and the auto key, which is essentially just the legend, is going to be a list, and it's going to be in the right. Yeah, so it's a little painful to specify these things. I just do a help to figure out what the parameters are if it's not doing what you want. Now I'm going to do a graphics off, because sometimes it buries these plots behind my windows, which is kind of annoying. Okay, so here is the breakdown, male and female, or female and male, and here's the legend, it's putting it to the right. So here we have this package will plot the density curves according condition and the covariate, and also plot the dots, the individual data points down here. You can see how things shake out. I think that's very useful. And let's do one more. In this one, let's break it down by multiple factors. Okay, so let's see. Quartz. Okay, we're going to do an XY plot and CSOA. We're going to use this data set called tinting, which I think has to do with window tints. Also in the DAG package, tinting car windows. Okay. The authors were interested in the effects on the window and vision and so forth. And we have all of these measurements. So let's do dim tinting. 9 measurements, 182 samples. Let's do names of tinting. Okay. CSOA. CSOA, what is that? Critical stimulus. The time to recognize a target in milliseconds. Okay. And IT is inspection time. The time required to perform a simple discrimination task in milliseconds. So let's take a look at the relationship between those. And I want to look at that and take into account sex and the age of the group. The data is the tinting data. Groups are the target. And the auto key, we're going to do the same thing. We're going to list it in 2 columns though. Okay, and now let's do the same thing. So let's see what this looks like. Okay. Alright, so now I've broken these categories down according to this interaction. And it's by sex and older and younger age group. And we're looking at the relationship between CSOA and IT. Let's take a look here at the same thing, but over that let's put in a smooth curve. Data tinting. So let's look at type. CP. Smooth. Okay. Alright, let's take a look here. Okay, here we go. So let's just take a look at this data a little bit more carefully. Tinting 1 through 10. Yeah, so the target, I'm not sure what that means, high con and low con. But it's breaking it by target and it's breaking the groups out according to this interaction. And then as far as this fitting of the lines, you can do a help XY plot to figure out what's going on there. Okay, so you won't be able to see this, but let's see. Those fields should be defined in here somewhere. It's a pretty long file, so okay. So that's kind of the basic idea. The major goal was to just give you an idea of how to do the plotting, how to take a look at your data using a few different tools. This is just, there's just some tools of many, and I encourage you to fool around a little bit more. But you should at least go through this. I'm hoping you went through it with me to get a feel for how to use the commands.